Okay, class will start. Let's look at the first question. So we have got this curve is defined by the parametric equations. Okay, we have got x and y in terms of the theta. So first part is to find out the dy dx, okay, is equals to cot half theta, okay, except for certain values for the theta, which should be identified. So for this one, we of course to find dy dx, we need to differentiate both dx d theta and dy d theta. Okay, we need to find out both. So from there, our dy dx is given by dy d theta over dx d theta. So we know that the dy d theta is a sine theta, and also the dx d theta is a 1 minus cos theta. So from there, because the proof needs us to give the expression in terms of the half theta, so in this case we'll have to make use of the double angle formula to help us lot. So from there, okay, we have the sine theta, okay, is equals to 2 sine half theta cos half theta. So we just use the usual double angle formula, but just we change the 2 theta to theta, and then the theta to the half theta. So we halve all the angles, okay, from the double angle formula. So same thing goes to the this one, okay, 1 minus cos theta. We use a double angle for the cos 2 theta, and we use a version that has the sine squared. Okay, so by using the same idea, we will have got this. So we can cancel off the 2 and the sine half theta, which this one will actually end us with the cot half theta. Okay, and we are supposed to find out what is the value of the theta that the dy dx is not defined. So in that case, okay, we will have because in this expression our denominator is is a sine half theta. So we know that for sine, okay, it is equals to 0, okay, when we have all the multiples of the pi. Okay, because when we have the denominator is equals to 0, this thing cannot be defined. Okay, so in this case we'll have got the half theta is all the multiples of the pi, in which the k all are here, all our integers. So in that case, our theta will be 2k pi lah, basically. Okay, so our 2k pi would take the value for the k, which are the integers. So we cannot have the theta is 0, 2 pi, 4 pi, or negative 2 pi, negative 4 pi, and so on. Okay, so that will be for our first part. Second part is to look at the point of the intersection of the curve. So and the line where we have y is equals to x. So in this case, because we have the relationship given, which is y is equals to x, so we equate the relationship, okay, for this y and x in terms of the theta. So once we equate that, this is what we get, and we just have to rearrange a little bit to get this. Okay, so we can see that we can actually get the equation which is in this form, theta equals to 1 plus something else. So if we actually look at this one that we have here, the something else that we get is sine theta minus cos theta, which is we want to express it in terms of the a sine theta minus alpha. Okay, so basically we use the harmonic form in the trigo. So this is what we usually do in trigo lah. So our sine theta minus cos theta is equals to this thing. Okay, a sine theta minus alpha. So from there, just do the usual thing. Okay, and we should be able to get the values for the a and also the alpha. So in this case, sorry, I made a mistake here. So the a here should be root 2. Okay, so that is what we do for part B lah. Okay, so for the question that is asked here, so for the double angle formula here, so whenever we have got, let's say sine 2 theta is equals to 2 sine theta cos theta, so we can actually just do any like multiple of these angles. So this is also valid lah. Okay, so even though we have got something like 3 theta, okay, we can also have this kind of the identity. So it actually works for all the angles. Okay, we can always adjust the multiples of the angle as long as the relationship between the angles are double of the other. Okay, so the double angle formula should work for all the angles. Okay, so that's the for our first question. Okay, for the second question, it's a bit long. Okay, we should look at how do we do this. So first is we have the curve y is equals to x squared intersect the line where we have y is equals to kx. The k is greater than 0. So the region bounded by the curve and the line, okay, between the origin and P is denoted by R. So show that the region is given by 1/6 kq. So for this one, right, so what do they really mean is that, okay, we have got this. This is our y is equals to x squared curve. And this line is we have y is equals to kx, and we are looking at the region for this one. So how do we find the region for this one is, of course, we integrate, okay, and get the area under the curve. Okay, so we need to know that the intersection point, so when we have this one, we have x equals to 0, and at this point, we have the value of the x is equals to k. Okay, so we are supposed to integrate, okay, this area under the curve for the line to minus the area under the curve for the this curve y is equals to x squared. So we have to minus them. So we use the upper curve to minus the lower curve, and we integrate them, and our values, okay, the limits will be from 0 to k lah. So which we are looking at this range from the 0 to k. Okay, so from there, what we have is we actually have the result that we needed to prove. Okay, so that would be for the first part. So second part, the line x equals to a cuts the region R into two parts of equal area. So we need to show that we have got this result, okay, this equation involving the k and the a. So for this one, it's not really a difficult thing to do. So instead of doing like one integration, now we have to do two integration already. So for that, now we have got x is equals to a is actually splitting these two regions into the same area. So what we have is, for the same integral, okay, which we are trying to find the area under the curve, now we have the area from 0 to a is the same as the area from a to k. So basically it's doing the similar thing like just now. Okay, so we already know what do we get after we integrate. So what we need to do is we just have to substitute, okay, the values when we have x equals to 0, a, and also the k. Okay, so from there just work with the expressions, and from there we should be able to get what we want to prove. Okay, basically is to work with the expression lah. Okay, so that would be for our part 2. Okay, so the third one. So the gradient of the line y is equals to kx increases at a constant rate with respect to time t. So given that we have got dk dt is equals to 2, so we are supposed to find out what is the value for the dA dt. So now we have got a new variable which is introduced into this relationship. So because before this we have been looking at the k and the a, so now we have one extra variable which is the t. Okay, so what are given is we have got dk dt, and also we have the dA dt. So when we have three variables involved, okay, we often need to use the chain rule. So in this case, if we actually try to relate that to the chain rule, so what we can do is we can actually have something else which we need to have dA dk or dk dA to relate these three things together. Okay, so how do we actually get the dA dk or the dk dA is that we actually have the relationship which we have earlier on, which we can actually use the relationship from the part 2 to find out what is our dA dk or dk dA. Okay, so let's say we are trying to find out what is the dA dk. So again, how do we actually get the dA dk? dA dk is we are trying to differentiate the relationship from part 2 with respect to k. Okay, so we have to use the implicit differentiation in this case already. So when we actually try to differentiate this, okay, with respect to k, so for the first one, k power 3, it's just 3k squared, okay, it's not difficult to do. And for the third term here, we have got 4a cubed. So 4a cubed, when we want to differentiate it with respect to k, we get 12a squared. So we differentiate the expression as usual, but just we have to multiply the term with the dA dk. Okay, so because we are differentiating a but with respect to k, so we have to multiply by dA dk at the end. And also for the middle term, because it's a mixture of the a and the k, so we have to use the product rule. So when we use the product rule, so what we do is, let's say we just keep the 6a squared for the first one. So for the first one, we keep the negative 6a squared and we are trying to differentiate the k. So differentiating the k will give us a 1. Okay, so that we'll actually have this term here. And for the other one, we keep the k, but we are trying to differentiate the negative 6a squared. So differentiating the negative 6a squared gives us negative 12a. But for this one, we are differentiating a with respect to k. So at last, we need to multiply the term with a dk, dA dk in this case. So basically after that is to tidy up. Okay, let's say we want to find an expression which is dA dk. So just rearrange all the dA dk terms in this case, and then we'll actually have this relationship here. So this is our dA dk. Okay, so now, okay, we are given the values where we have a is equals to 1 and k is equals to 2. We are able to find out what is the value for the dA dt in this case. Knowing that the dA dt is dA dk times the dk dt. So earlier on, this value is our dk dt given. Okay, so basically it's just substitute all the values of a and k into our dA dk. So this is what we do, we substitute in all the values, and at last just evaluate a value for that, which we actually have the dA dt is equals to a half. Alright, so that would be for our third part. For our part 4, okay, so determine the value of the dA dt when we have a is equals to 1 but k is not equals to 2. So express your answer in the form of this p plus q root 3, okay, where our p and q are integers. So in that case, right, we need to find out first, because they say when we have a is equals to 1, we have some other value of the k which is not equals to 2. So from there, what we need to do is we need to use the second part again, okay, because second part gives us the equation which involves a k and a. So from the second part, okay, we use a relationship to find out what is the value of the k log. So for this one, it is already given the a is still 1. Okay, so when a is equals to 1, we actually end up with this relationship of the k. So this is the equation of the k. So from part 3, we know that when a is equals to 1, the k can be equals to 2. So we know that in this case, the k minus 2 is a factor to this equation. Okay, so we just do some long division, okay, and we will actually find out another factor for this relationship. Okay, so from the long division, we know that another equation that we get is actually k squared plus 2k minus 2 is equals to 0. Okay, so this is what we will get from there. So from there, of course, we want to solve the value for the k log. Okay, so by using quadratic formula, if we want to use the complete the square, we will actually get two values of the k. Okay, so these are the values of the k that we need to substitute, okay, back into the dA dk to get the value for the dA dt. So we have got two sets of the value to consider. So let's say first we consider the value for k is equals to -1 plus a root 3. So basically nothing much, okay, but here we just have to substitute the a and k into the dA dk again. So when we substitute the value into the dA dk, we have got a lot of things to work with, okay, which is we have got in our dA dk, we will actually end up with something that has a root 3 in our expression. But usually we do not like to have a square root, okay, in our denominator. So what we do is we have to rationalize it by multiplying with the suitable expression. So we can multiply with something like the conjugate of the denominator. So instead of the negative, we multiply with a plus version to it to eliminate the denominator in our to eliminate the square root in our denominator. Okay, so from there, okay, just tidy up the stuff, we will actually get some nice value, which we get half plus half root 3. So this half plus half root 3 is our value for dA dk, but we want to find what is our dA dt. So in that case, our dA dt is dA dk times dk dt. So our dA dk is what we have found earlier on, and k dt is still 2. So from there, we can actually get the value for the dA dt is 1 plus root 3. Okay. So after that is basically to do the same thing, but we do it for another value of the k, which is negative 3 minus 1. So somehow, okay, at the end, we should end up with something like this, okay, which we still have square roots in our denominator. So we have to multiply with the conjugate lah to rationalize it. So we will actually end up with the dA dk is this value. And to find the value for the dA dt, we just have to use the chain rule again, and this is the value that we actually get. Okay, so for this one, you can do it slowly on your own. The idea is the similar. Okay. Next one. So for next one is to find the dy dx. Okay, given that we have this expression, y is equals to 2x minus 3 times e to the power of negative 2x. So for this one, it is not difficult to do as long as we use the product rule. Okay. So to use the product rule, we will actually end up with this expression where we have 8 minus 4x times e to the power of negative 2x. Okay, so determine the set of the values of x for which y is increasing. So when y is increasing, we know that the dy dx is greater than 0. So when we have dy dx is greater than 0, okay, this expression is greater than 0. Okay, but we know that for the exponent term, okay, we have got this e power negative 2x is greater than 0. So we will only look at this part, okay, which is 8 minus 4x is greater than 0. So from there, just solve the inequality. Okay, we will get the x is less than 2. Okay, so this should be quite straightforward lah. But just have to take note that the property for the exponent term. Okay, next one. Okay, so for this one, we have got the functions, okay, ft is given by this expression, and show that the df dt is given by this one. So it's not difficult to show that for the df dt, okay, as long as we use the differentiation correctly, and we also what we can do here is we can actually expand. Okay, that will be easier for us to do the differentiation. Okay, so when we actually do the expansion, we will actually have the second term here is a 2 sine 2t. Okay, so from there after we differentiate, we actually have this which is a 2 sine 2t, because after we expand here, we should get 2 cos t minus 4 sine t cos t. Okay, so when we actually differentiate, okay, we should actually get the result which is like this. Okay, sorry, I'm referring to this one. Okay, so we should be able to get the result lah, because it's already given anyhow. Okay, so let's look at the part 2. Determine the range of f. So how do we actually usually look at the range of f is that, okay, let's say we have got the fx is equals to a certain function. So how do we look at the range of f is we will actually look at what is the value of the function that it takes. So let's say the function, the fx looks like this. So how do we determine the range is we actually look at the highest and the lowest value. So this one will be the range of the fx. Okay, so the idea is similar to this one. We are looking at the range of the f. So how do we actually know that is there any maximum or the minimum value for this range is by looking at the turning point. So the turning point is basically their maximum or the minimum point. And for this one, that could be, okay, I repeat, that could be their highest and the lowest point, okay, before we find out what happened. So for this one, okay, we just try to find out what is the highest and the lowest point, or rather we say it's a maximum or minimum point. So to check their maximum or the minimum point, of course, we let the df dt is equal to 0, okay, and we try to solve, okay, what are the values of t that gives us the highest or the lowest value, which is what we mean here is the maximum or the minimum point. Okay, so for this one, okay, we check for each value for the t and see what is the value of the ft that it gives. So just in this case, we sub in all the values of the t and find out, okay, what are the maximum or the minimum point. So for this, okay, the maximum or the minimum point that we could identify is -3 and also 3/2. So far this is our maximum or the minimum point. Okay, but there is something that we have to be careful is that we also need to check for the starting point and the ending point, because for this function, it is given that we have got 0 to 2 pi. Okay, we are not sure, okay, how this function looks like. Because, okay, although it is given that we have got these two values, right? So in this case, the -3 is our minimum point, 3/2 is our maximum point, but we are not sure whether that would be our range or not. Because for some function, we might have something like this. Okay, so let's say these are the this is the domain of the function. Okay, so even though we already identify, okay, what is the maximum and the minimum point here, but they are not necessarily our range, because the range look at this and this value, so this will be the range. So by looking at the maximum point and the minimum point, so this one are not the range. Okay, so we have to check whether we have got any other values, okay, which in this case is our ft, which is higher or lower than our maximum or the minimum point. Okay, so to do the checking, we just have to sub in the starting point and the end point for our domain. So in this case, the domain given is from 0 to 2 pi. Okay, so when we sum in the endpoint, we have got the f0 and the f2 pi, they are both 1. So it means in this case, the starting point and the ending point are in between these two maximum or minimum point. So in this case, how would they look like? So they will look like something like this. So let's say this is 0 and this is 2 pi, right? So they might, okay, look like something like this. Okay, we have the -3, right? So we have got, okay, this is 1, let's say. This is 3/2, and this is -3. Okay, so what it could look like, it could look like something like this, because we have got one maximum point and also one minimum point. Okay, so it could look like this. Okay, something like this. So in this case, the range is determined by the maximum and the minimum point. So we are safely to use this maximum or the minimum point as the range. Okay, so that will be the range for this curve. All right. So that will be for our second part. For the third part, we have got curve C is given by this equation. Parametrically, so x is this expression and y would take the previous expression. So first show that x squared plus y squared is equal to this relationship. So it is not difficult to show as long as we sub in the x and y in terms of t, and then we square them, and then after we square them, we will have got all the terms which is like cos square and sin square. Okay, so that will actually gives us a 1, and for this one, okay, it is actually our compound angle formula. So this is a compound angle formula for sine 3t, which is sine t plus 2t. Okay, so this will be our sine 3t at the end. So it is not difficult to actually prove it. Okay, for the part 3. Part 4. Deduce that C lies between two circles, okay, centered at the origin and touches both. Okay, so how do we actually do this is that we have got x squared plus y squared equals to something. Okay, so what is again the x squared plus y squared? So x squared plus y squared is somehow the equation of a circle which has a center which is at the origin. Okay, and at different, because the t is changing, right? The t can be from 0 to 2 pi. So at different value for the t, okay, if we actually try to change the value of the t, we will actually have the radius of this circle is changing. Okay, so what do we mean by that one is, if we have, this is a circle, and by changing the t, okay, we will actually have different points. So this is a specific value for t, we will have this value for the x squared plus y squared, because for a circle at the origin, as the center, we'll have x squared plus y squared is equal to r squared. So in this case, the r squared will actually take different value, okay, depending on, so this is the value for first t, this is for another t, this is for another t, and so on. So if we have different values of the t, the r squared will actually gives us different value. Okay, so we are supposed to prove that the curve C, which consists of different points, and in fact it is a curve. So this curve actually lies between two circles centered at origin and touches both. So how do we prove that? Is that, okay, for the t, because we know that we can actually have different values of the t. Okay, so if you look at the right hand side of the x squared plus y squared, which would be our r, okay, so in that case, that would be, we know that for any sine function, okay, the value is from -1 to 1, okay, if we have from 0 to 2 pi based on the t here. So this one, okay, sine 3t, okay, we just have to try to make it in terms of the 5 plus 4 sine 3t. So what do? Is we times 4, then we get this relationship, okay, and we just have to plus 5 to all the terms to get this. Okay, so our 5 plus 4 sine 3t is in between 1 and 9. So what is basically our 5 plus 4 sine 3t is? That is the value for the x squared plus y squared. So in this case, the values of the x squared plus y squared is in between 1 and the 9. Okay, so in this case, because we know that the x squared plus y squared is equal to r squared, right? So our r squared in this case, okay, is in between 1 and 9. So it means the r is in between 1 and 3. So for all the points on this curve, okay, we'll actually have the points, okay, which is always in between this r is equals to 1 and r is equals to 3. Sorry, I made a mistake here. This one should be 3. So at last, okay, what does it mean is, we will have got, okay, this is the circle which we have radius 1. This is the circle that has a radius 3, okay, and then all the points that we have is like, we will actually have all the points which is like in between these two ranges here. Okay, so you can actually use the plotter to check this curve. You can actually use the plotter to check the parametric equation for this, and you can actually plot the graph and see that the curve is actually in between the two circles. Okay, so for that, we actually look at the next next part of the question. So part 5, find the gradient of tangent to C at a point for which t is equal to 0. Okay, so for that, what we have is, okay, when we have the t is equals to 0, okay, we need to find out what is the dy dx in this case. So for that one, we need to differentiate, okay, we get the dy dx, and we substitute the t equals to 0 in, and we should be able to get the value for the dy dx. Okay, so this one I didn't work that out, but you can always do that lah. Okay, it's quite easy to do, right? So we actually need to look at other questions now. Okay, so okay, for the next question is they gives us a parametric equation which is x and y in terms of t. So to prove that this dy dx is given by this expression, so for this one it's just we have to really be careful in differentiating. So before we can find dy dx, we need to find dy dt and dx dt. So to find the dy dt and dx dt is, we have got dx dt. So for all these expression, right, it is easier for us to express that in terms of the brackets with a single power. So by this, it is easier for us to differentiate. So how do we differentiate this x? Is move down the power. Okay, we move down the power, and we have this is the power after we minus 1, and we still have to multiply that expression by differentiating inside the bracket. So differentiating inside the bracket, we get -1. Okay, so this is the expression for our dx dt, and do the same thing for the dy dt. Okay, so we are able to show what is the dy dx. Okay, and the next part is to do the expansion for dy dx. So the dy dx, which is 1 plus t, okay, over square root of a 1 minus t squared, can be written as 1 plus t times a 1 minus t squared to the power of negative half. So from there, we just have to do, okay, the binomial expansion as usual. Okay, I think you should be able to get that. So this is the result, okay, after we expand up until the term which is like t power 4. And after that, we want to estimate the gradient. So just substitute the t equals to 0.5 into our dy dx expression, and we should be able to estimate the gradient. So the gradient in this case is 1.71. Alright. So that will be our part 2 for the question. Okay. So next one. So find the equation of all the horizontal tangents to the curve equation, which is a y squared is given by this expression. So horizontal tangent is where we have dy dx is equals to 0. Okay, so this is not difficult to do basically. So first is to differentiate this implicitly. So what we do is we ddx to both sides. Okay, we ddx to both sides of this equation. For the right hand side, it's very easy to differentiate. For the left hand side, okay, we have to differentiate y squared with respect to x. So what we do is we differentiate the y squared as usual, then we get the 2y, and then we have to multiply by the dy dx because we are differentiating a y, okay, not an x. So basically, we are looking at the tangent, okay, so the tangent occurs when we have dy dx is equals to 0. So in this case, the whole left hand side here will be equal to 0 already. So after that, the work to actually solve for the x is not difficult. So once we have got these two x already, okay, we substitute it back to the earlier equation. Okay, back to the earlier equation here, and we are supposed to find out what are the values for the y. Okay, in this case, take note that because we have got y squared, right? So the value for the y, okay, at the end should have a plus and minus, okay, because we are solving for the y squared is equals to, in this case, 6 and 36 and 9. Okay, so when we root them, okay, we should consider the plus and minus. Okay. Next one. So this diagram is the curve with this equation x in terms of y, where this curve crosses the y-axis at a and b. So first, find an expression for dx dy. So this is something that is also quite usual. I mean, it's an equation still, but just the interchange of x and y, and now we just have to find the dx dy. So it's just doing the same differentiation, just that they interchange the x and y only. So instead of looking at dy dx, now we have dx dy. So it's not difficult to do. So for this one, because we have got two terms, it's a product, so we have to use the product rule accordingly. So differentiate y minus 4, we get a 1, and we fix the ln 2y plus 3. And then the next thing is we fix the y minus 4, and we differentiate the ln 2y plus 3. So how do we differentiate the ln 2y plus 3 is we put the 2y plus 3 in the denominator, and we differentiate the 2y plus 3 and put in the numerator. That is it. So you just have to tidy up a little bit. Basically, that is the expression for dx dy. Okay, so part 2, find the exact gradient to the curve at the point which we have a and b. So if we actually look at the figure again, the a and b are actually our y-intercept. So at these 2 points, we will have x is equal to 0, and we are supposed to find the gradient. Okay, so just have to take note, the gradient is dy dx. Okay, but we have dx dy. So later we have to 1 over the dx dy to get the values. Okay, so what we have is, because we know that at the 2 points the x is equal to 0, we need to find out what is the y coordinate for both points first. Okay, because our dx dy are all in y. Okay, so when x equals to 0, substitute that into the first equation, okay, of the curve. We actually have two values of the y by solving from there. Okay, so substitute these y's, okay, into the dx dy. We have got these two values. Okay, substitute the values of the y into the dx dy, and if we want to get the value for the dy dx, we need to 1 over that. Okay, so this is why we actually have these two values for the dy dx. Okay. Next, okay, we actually look at the question which this curve C, okay, is given parametrically by this x and y, and show that the dy dx is equals to 3/2 cot x cot theta. So this one is not a difficult thing to do, okay, because dy dx is just dx dy d theta over dx d theta. Okay, so I think we all should be able to prove this. Okay, so second part, a tangent to C, okay, intersect the x-axis and y-axis at the P and Q respectively. So in this case, they say we have a tangent line. So this tangent line intersect the x and y at P and Q. So in this case, what happened to this one is the P and Q are the x and the y intercept, okay, of this tangent line. So first of all, we need to find out, okay, what is the equation of this tangent line. So in order for us to find the tangent line, okay, we have to use y minus y1 is equals to mx minus x1. But here there is no point given for our x1 and x2. So if there are no points given, we will have to use a general expression for the y1 and x1. So what are our y1 and x1? They are just this one, because x1 and y1 can change anytime, okay, according to the value for the theta. Okay, theta changes, x and y changes, the x1 and y1 in the equation of our tangent is changing as well. So we just make it general. Okay, so to make it general, we substitute the y1 and the x1, and not to forget our the dy dx, okay, the gradient. So basically is we can actually tidy up a little bit. So when we tidy up a little bit, and for this one we can actually try to because this cot theta is a cos theta over sin theta, so we can multiply this whole equation with the sin theta, and we actually get something which is nicer to work with. Okay, and another good news is that we just have to collect the x and y together. So this is our x, this is our y term, collect them together, and the rest just throw it to another side. So we have got 6 sine squared and 6 cos squared. So the good news here is we actually have this, okay, 6 times in a bracket sine squared plus cos squared, which will only gives us a 6. So it is not too bad. We actually have a tangent line, which is quite nice. Okay. So next, how do we actually find the P and Q? So the P and Q are our x and y intercept. Okay, so the P is an x-intercept, which our y is equal to 0. So when we have y is equal to 0, we can actually get a relationship for our x. Okay, so in this case, the x is a 2 secant theta. For Q is our y-intercept, so y-intercept in x is equal to 0. So we can actually get an expression for y. So these two are our P and Q. Okay, so how do we get the midpoint of PQ? The midpoint of PQ is just half of the x and the y coordinate for the P and Q. So this is how we can prove the midpoint of the PQ is given by this expression. Okay. Alright, so for part 3, so hence show that the midpoint of PQ lies on the curve where we have this, okay, 4 over x squared plus 9 over y squared is equals to 4. Okay, so what happened there is because we have got the midpoint, okay, it's actually we have the point which is this is our x, this is our y. Okay, and for this midpoint, right, they are actually our x and y coordinate, but again the x and y coordinate actually depends on the value of the theta. So again, by changing of the value of the theta, we will have different values for the x and y. So different values of the x and y will actually form somehow like a curve. Okay, by changing the theta, we actually have a curve for the x and the y. Okay, so how do we actually relate the x and y is that we actually have to use the Trig identity. So if we look at first one, we have got x is equal to secant theta. We try to express it in terms of cos theta. So same goes to this one, y is equal to 3/2 cosecant theta. Try to make it in terms of the sine theta, because we can actually relate them, okay, by using cos squared plus sine squared is equals to 1. So just substitute the values, I mean the expression for the cos and the sine into this, okay, identity, and basically just tidy up by multiplying 4 to the previous line. So this is how we actually prove the curve. Okay, so that would be for this question. Okay, last one. So find the coordinates of the stationary point of the curve with this equation where we have y is equals to ln x minus kx and determine its nature. So for the first part, it's actually not difficult to do. We just have to differentiate, okay, for this y is equals to ln x minus kx. Okay, for this one, right, what we have is we just have to differentiate, and it's not difficult to differentiate dy dx. And since they ask us to find out the nature, so for this nature, we'll actually have to find out the d square y dx square, which is again is not difficult to find. So, okay, we need to find out what is the stationary point or the turning point. So the turning point is when we have dy dx is equals to 0. So when dy dx is equals to 0, we can actually solve for the x very easily. So the x coordinate is 1 over k. But they need the coordinates, right? So we cannot just find the x, we need to find the y. So just substitute the x into the equation again of the curve. So we'll actually get the y is equals to ln of 1 over k minus 1. So give the coordinate of the turning point. It's not difficult to do. Next is to identify the nature. So the nature is to sub the x into the d squared y dx squared. So when we substitute the x into the d squared y dx square, we will actually find out the value for the d squared y dx square in terms of k. That would be negative k squared. And because the k squared is something positive, okay, and we have a negative k squared. So for this one, it is a negative value. So if our d squared y dx squared is less than 0, so this stationary point is a maximum point. Okay, so that will be our first part. Okay, for the second part, okay, hence show that this equation, okay, ln x minus kx is equals to 0 has real root when we have this condition for the k. Okay, so although it is 2 marks, but it actually requires us to actually think a little bit about that. So, okay, what happened for that one is, okay, why do we have this equation? If we compare this with the original equation for the curve, it means we are looking at y is equals to 0. So, what is y equals to 0? The y equals to 0 is the x-intercept. Okay, so if we relate that if we have this equation has real root, so it means it has x-intercept. Okay, so when it has x-intercept, it means the curve will touch the x-axis. Okay, so how do we know about this curve? How do we know about the property of this curve? Is that by using the previous information. So previously, okay, what we have got is we have got one stationary point. Okay, in fact, this is a maximum point. So if this curve has only one maximum point, so this is the shape of the curve roughly. Okay, so what do we need to do for this curve is that this curve, okay, will only have x-intercept if this is the case. Oh, sorry. So it has at least, so this is in this case, it has one intercept. In another case, it could be something like this. So it has more than one x-intercept. So for both cases, they have real roots. Okay, when we actually have the equation, which we have this one, the ln x minus kx is equals to 0. Okay, we are looking at the x-intercept. So what is the condition for this curve, okay, to be in these two situations here? Okay, so the important point is this one, the maximum point. So in this case, the maximum point, or in particular, the y coordinate of this maximum point must be greater or equals to 0. So this case is when, this case is when the y coordinate of the maximum point is equal to 0. This point is when the y coordinate of the maximum point is greater than 0. So we need to have the y coordinate, okay, of the maximum point is greater or equals to 0. Okay, so we can solve from there. So we have ln 1 over k is greater or equals to 1. So it means the 1 over k must be greater or equals to e. means in this case the k is less than or equals to 1 over e. Okay, but why is it that we have the 0 in the question that we are supposed to prove? Is because it is already given earlier. So this 0 actually comes from here. We must also make sure that the k is greater than 0. So by considering the k is greater than 0 and the inequality that we have found just now, okay, we will actually have this inequality that we are supposed to prove. Okay, so that will be for the for this question. Okay, so I think we still have a little bit of time. You give me a few minutes. I'll actually sketch for you the curve for the one just now. Like for this one, the part 4. Okay, I'll sketch this curve for you. Just give me a minute, and you actually understand the idea better. Okay, just give me a minute. Okay, so you can actually look at this, wait a minute, so we can actually look at this curve here. So, okay, from what we have for this curve is that, you see this red curve is the equation that we have plotted for the parametric equation, the x and y in terms of t. So, from the question, what we are supposed to prove is, we're supposed to prove that that curve, which is in red, okay, will be in between the two circles. So just now from what we have proved, that is, we have already proven this curve is in between the two circles, okay, which has the radius which is 1 and 3. Okay, so by looking at this, you actually see how does this curve looks like. Okay, the blue one is the circle that has a radius 1. The green one is the circle that has the radius 3. And then all the points on this red curve, which is the parametric curve, the curve C, okay, is actually in between these two curves, and some points that are actually touching the circles. Okay, so this is why we have this result for part 4. Okay. All right. So from okay, by that I think that is it for the discussion today. Okay. Okay, so I guess that is the end for the discussion today. So I'll see you tomorrow. Thank you.